when a stone is thrown into a lake, it forms a ripple, and the area of the ripple is given by this formula in terms of time. So to find the rate of increase, after 3 seconds, we first find the rate by differentiating A. So dA dt equals to 8 pi t. So that's the formula for the rate. And after that, we're going to substitute t equal to 3 seconds in order to find the rate. So we'll do 8 pi times 3, which is 24 pi. And the formula, this is square meters, so it will be square meters per second. Right, so it's like that. So we did that on Monday, one lesson ago. So in the extension 1, I should say extension 1. In the extension 1, we have problems that involve more than one variable that changes. So in this case, only the area changes. But now there could be more than one variable that change, y and x, for example. So we're going to use the chain rule in order to calculate the other rate of change. This is the chain rule. Let's look at how this chain rule works. So if I want to find the rate of change of y, dy over dt, all I have to do is to separate that into a product, put dy here, put dt here, and then you just insert the second variable in. Right, the dx gets cancelled. So we're going to use this rule to help us to find out the rate of change of y. Or if we are given the rate of change of x, or vice versa, given the rate of change of y, find the rate of change of x. Okay, so we're going to use this formula to do the second problem, the first problem. Okay, example 1. Okay, I'll just show this again. Alright, a spherical metal ball is heated so that the radius is expanding. Radius expanding at this rate. Okay, so if we let the radius be r, the rate of change of radius can be written as 0.04. Okay, let's include the units, millimeters per second. And at what rate will the volume be changing? So it's asking dV dt is question mark. So given the rate of change of radius, what's the rate of change of volume? When the radius is 3.4. Okay, that's the problem. So what we're going to do is to use this formula I just introduced to you. So to do that, we're going to find out what dV dt is. So we're going to start off writing dV dt equal, right, like this, dV dt equal to something times something. Put the dV here, put the dt here, right, because dV dt is equal to something times something. Just put the dV on the first fraction and dt as the denominator of the second fraction. In between, because it has related to r, the volume is related to r, write dr here, dr there, right? That's your rate of change formula. Okay, so obviously we have dr dt. That's taken care of. We got the value there. We don't know what this is, question mark. But we can find out what dV dr is. How to find dV dr? We need to know the volume of the cylinder because it's a spherical metal ball. So the volume of cylinder is, so in this topic you need to know all the formula for the volume, surface area, etc. is pi r cubed, or 4 pi r cubed over 3. And we need to use this because we have to find dV dr, because V is in terms of r. That's why we could find dV dr. So to find dV dr, we have to differentiate V in respect to r, which is equal to 4 times 3 pi r squared over 3, which is, oops, I got the 3 there, 4 times 3, which is equal to 4 pi r squared. That's the dV dr. So you're going to substitute both of these into the formula. Okay, this and this. Alright, let's substitute this information in to find dV dt. So 4 pi r squared multiplied by 0.04. Now we are also given the fact that r is 3.4, so you substitute 3.4 in as well. See that 3.4 needs to be replaced. And put everything in. 4 pi, that's squared times 0.04. And you just do it on a calculator. Got my calculator here. So 4 pi, shift pi times 3.4 0.04 squared times 0.04. That gives you 5.8 as expected, 5.81. So there's the answer for you to check. 5.81, 5.81 approximately. The volume for the unit for volume will be cubic millimeter because it's volume every second. That's the rate of change. So given the rate of change of the radius, I could find out the rate of change of volume. Okay, like that. So it's very easy. So you just have to use the rate of change formula. So this part can only be tested in extension 1. So this is in extension 1 only. So you won't be asked this sort of question in TUNET, extension 1 only. Okay. So in TUNET, you just do basic things like A in terms of T to differentiate, very easy. But in extension 1, there's 2 variables, one volume and one radius. Okay, so note the working, very easy. Okay, good. Once you finish, we can do another one. Could try the question on the next page using the technique. Okay, good. So we're going to do the next page. Okay, so look at another problem about volume of water given by this formula. So this time the formula is given. Unlike the other one, you have to find the formula of its speed. So this one, the formula is given, where x is the depth of water. The pool is filled water at this rate. Okay, so that means this is the information about volume. Write it down, dV over dt is 1.3 cubic meter per hour. Per hour this time instead of per second. So we're given dV dt. At what rate will the level of water be increasing when the depth is that? So you have to find the rate of the level of water, which is x. Find the x over dt, question mark. And then what else are there? And then when the depth is x, which is 0.78. Okay? So summarize the information in terms of dV dt, dx dt, and x or whatever. Write all of these down, and then we're going to use it to find the x dt. So we're going to write this down first. We're going to find, so because we're finding the x dt, so we can write dx dt equal like that. Again, write it as a product of 2 fractions. And then when you write it as a part of 2 fractions, the numerator goes in the numerator of the first fraction. The dt goes in the denominator of the second fraction. And the thing we're trying to find, and it's related, the level of water is related to the volume. So put the dV here, put the dV there. There's the equation we're going to use. Okay, we got dV dt, that's taken care of, 1.3. We do not have dx dv, that's where the formula becomes useful. So let's find out what the x dt is. So we'll first find out what v is. And to find the x dv, we have to make x a subject. That's too hard. So what we're going to do is to find dv dx first. And then we can find the x dv. To find dv dx, you differentiate in respect to x, which is 2 plus 6x. And why is that useful? Because the x dv is just the reciprocal. So if we reciprocal the fraction, it becomes 1 over 2 plus 6x. Like that. And then we can just substitute. So we got everything. So 1 over 2 plus 6x, which is the x dv. dv dt is 1.3. And in addition, we have to substitute the 0.78 into x. And then we can calculate the rate of change of the level of water. Yeah. Rate of change of level of water, 0.78. Okay, good. Yep. And then we're going to substitute 1 over 2 plus 6 times that, times 1.3. Let's use our calculator. You type in a fraction, 1 over 2 plus 6 times 0.78 times by 1.3. 0.1946. Okay, so we'll correct to, don't say, just correct to 3 decimal place. 195. Okay, good. 0.195. And the units for level water, because volume is cubic meter, the level water must be meters. And remember, the rate of change at the beginning is per hour, so it has to be per hour here. Done. Okay, all good? All right, so it's very easy. It's very methodical. If you follow this procedure, it always works. Okay, so you need two things: the rate of change of one quantity, the formula that connects the V with the other quantity, and then you can find the rate of change of the second quantity using this rate of change formula, which is really the chain rule. Okay, all right, good. Once we do that, we're going to move on. So we'll do another one. Okay. All right, we'll do example 3. So this one will involve a cone. So again, you need to know this formula well, how to find the volume of a cone, surface area of cone, etc. So let's look at example 3. Okay, let's look at the question. So a vessel containing water in the shape of an inverted right circular cone has a base radius of 2 meters. Okay, so that means that shape has 2 meters. That's the radius of the cone, a height of 5 meters. Okay, so we got these two things, 5 meters, label it there. That's the shape of the cone. Water flows from the apex of the cone. Apex is this thing. This is called the apex. Apex, just the apex of the triangle. So the water is flowing out. Flow out from that apex. At a rate of 0.2 cubic meter per minute. So this is a thing about volume. So you may write, let V be the volume of water, not flowed out, but volume of water in the tank, in the cone. Okay, so that means this is a rate about the volume, which is 0.2 cubic meter per minute. But remember, because water is flowing out, the amount of water inside the cone is decreasing. Okay, so put a minus because volume in the cone, water in the cone decrease, right? Because it's flowing out. So you have to use some common sense here. Water decrease. Okay, good. All right, so what do we do next? What do we do? Okay, good. So we got the dV/dt. So is find the rate at which the water level is dropping when the depth of water is 4 meters. So we have to find level of water. So maybe if that's the water, so maybe water, that's the water. So that's the level of water, H. So let H be the depth of water. Okay, so you have to introduce some pronumeral. So H be the depth of water, and you have to obviously find the dH/dt when the depth of water is 4 meters. So basically, when you read the question, you have to change it all to mathematical symbols. The dV/dt, you're finding the dH/dt given H is 4. So now we have a problem to solve. So let's write down the first thing is we're going to find the dH/dt. So we start with the dH/dt equal. Actually, you don't have to start with something you have to find. You can start with something you know. Let's start with the dV/dt, right? dV/dt equals to dV something times dt. And you just put dH in the middle. Right? So you can do it like that. You don't have to start with dH/dt. You can start with dV/dt. Okay, so you get the same thing. What do we do next? So we got the we got dV/dt, which is over here. That's dV/dt. That's taken care of. We have to find dV/dH, which means we need a formula of V in terms of H. Okay. Now this is the hard part, finding the formula. So in the previous one, formula is given. The first one, the formula is easy. The last one, the formula are not easy. You have to actually derive it. So what we need to do is, the volume of the cone, the volume of water is in terms of it's a cone, isn't it? So let's call the radius r. Okay, so the volume of the cone of the water inside the cone is 1/3 pi r squared h. But there's a problem there. There's now 3 per numeral: volume, radius, and h. So what we need to do is to get rid of the r. Okay, there's too many per numeral. So you have to find r in terms of h, which means we have to look at the geometry of the cone. If you look at it more carefully, this is actually, there's some similar triangles. Let's draw it again. So we've got this shape, which is 5, 2, and 5, right? That's the original cone. And then we have inside the cone, inside the triangle, there's another triangle. The height is h, and the radius. So we can use similar triangle to express r in terms of h. So we'll do the ratio matching sides. You don't need to prove they're similar because it's too much work for one question. I think you can just assume it. And it's not hard to see why they're similar. They have the same angle, both right angle. They share a common angle. They're equiangular, isn't it? So the matching sides are in the same ratio. You just need to know where's the matching side. So r matches with the 2, whereas h matches with the 5. Easy. And we're going to find r in terms of h. So we're going to multiply both sides by 2 times by 2. So therefore, r equal to 2h over 5. Once you get r in terms of h, we can substitute that into the volume of the cone formula. So the volume will be 1/3 pi 2h over 5 squared times h. So it's everything in terms of h. Okay? So when there's another polynomial, you have to somehow find the other polynomial in terms of the one you're trying to differentiate in respect to. So that's the hard part, which is not that hard because if you look at it, the similar triangle can easy to see. Okay, all right, let's continue. So we're going to square this, which is 4h squared and times by, so 4h squared over 5 over 25h pi 1/3. And then what you're going to do, you're going to continue. You get 4 pi h cubed over 75, like that. And now we can differentiate. So once you find v in terms of h, you can find dv dh. dv dh. So dv dh is 4 pi over 75 times h 3h squared, like that. And the 3 cancel with the 75, which becomes 25. So we cancel, which is 25. 25 at the bottom. 4 pi h squared, like that. Okay, once we do this, we're going to substitute this into the formula there. So we're going to substitute this bit over here. Okay, so it's d 4 pi h squared over 25 over here. 4 pi h squared over 25 times dh dt, which we don't know. But we know what dv dt is. dv dt is negative 0.2. Okay, so now we just have to solve for dh dt. Okay, so let's solve for dh dt. So dh dt can be found by multiplying both sides by 25. So negative 0.2 times by 25 over 4 pi h squared. Okay, so for dh dt, and then you have to find the rate when h is 4 meters. Okay, so substitute h equal to 4. So that means dh dt equal to negative 0.2 times 25 over 4 pi times 4 squared. Okay, and then you just do on a calculator. So 0.2 times 25 divided by 4 pi times 16, close bracket. Different. Centimeters. That's right, because it's centimeters. Okay, good. That's in meters. That's okay. So right, equal to 0.0248, 0.0249. Correct to 3 significant figures. Negative meters per minute, like that. And the answer C is in centimeters. Okay, so you can convert that to centimeters, which is equal to negative 2.49 centimeters per minute. So what that tells you, the negative tells you that the depth of water is decreasing at 2.49 centimeters per minute. So write a conclusion. So to interpret the meaning of negative, negative means the depth of water is decreasing. So yes, so as you can see, the concepts are not hard, but the hard part is actually doing the derivation of the volume in terms of H. I think in the exam question, they probably will ask you to prove it, so people are not disadvantaged to attempt the later part of the question. But note the techniques, these techniques are examinable in the test, in the trial, or in the HSC. Okay. And it will be, you get the opportunity to do this sort of question in the textbook as well. Alright, so we did the first three. Let me see, maybe we'll leave some out. Maybe we'll leave some out and then we'll do another one. How much time have we spent already? Spent 20 minutes, yeah, otherwise we're going to sit there for too long. Okay, we're going to look at another question, maybe example 5. Skip number 4, you could try that by yourself. Do example 5. Should we do, yeah, maybe example 5. And then example 7 we'll do. And then we'll do maybe example 8. Okay, alright, we'll do example 5. So the next one you try by yourself. It is a bit hard, but I think it's been asked in the past HSC. One of the past HSC questions of which I forgot. So you could check this out later on from a Success One book. This one we'll do, because this one's a bit different. Okay, have a read. Example 5. Okay, a 10-meter long ladder has its upper end against the vertical wall and its lower end on the horizontal ground. Let's draw a picture. So we'll have a wall, we'll have the ground, and we'll have a ladder, which we represent by a straight line, and that ladder is 10 meters long. Okay, so basically the lower end is slipping away at a constant speed of 4 meters per second. So this thing is moving away at 4 meters per second. Find the rate at which the upper end of ladder is slipping down the wall when the lower end is 6 meters from the wall. So when this is 6 meters, what's the rate of change of at what rate does this slip down? Okay, question mark. Okay, so they gave you a hint. Let the lower end of the ladder is X meters from the wall, the upper end Y meters above the ground. So we're going to use some pronumeral. In this case, we represent this length be X, represent this length be Y. Okay. So basically, we're given, from here, we're given dx dt is 4 meters per second. And we're going to find dy dt, isn't it? So we're going to find dy over dt, question mark. At what rate is it going downward? Rate of change of y, when x is 6. That's what we're given. So what we do is we start off with dy dt. That's what we're going to find. Write it as two fractions, so dy over here, dy dt over here, and put the dx on both of these. Okay. So we've got dx dt, that's taken care of. We have to find dy dx. So we need to find a formula between x, y, and you have to consider the geometry of this shape. And this is a right angle triangle, so the only equation we could write down is Pythagoras theorem. Okay, so we've write Pythagoras theorem, which is x squared plus y squared equal to 100. We're going to make y the subject before we differentiate, 100 minus x squared, and then we're going to square root it. We'll take the positive square root because y is positive, it represents the length. And maybe write it without a index, in index form, half. Okay, let's differentiate it. So we'll go dy over dx. So dy dx Actually, I'll leave that room for, okay. dy dx, you have to use the chain rule. Bring the half down, 100 minus x squared to the power negative half, like that. Then differentiate what's inside, which is negative 2x. Get rid of the 2. And then you're going to write x, that will be 1 over square root times by negative x, which you can put at the top, on the top. Okay, so we've got this expression for dy dx, which will be used in the related rate of change formula on the top here. So we're going to substitute that onto the top, and then we substitute. Okay, so note how I use the chain rule, differentiate the power, bring the power down, subtract the power by 1. Differentiate what's inside, which is a negative 2x. Write it without index form, write it insert form, and you get that. Let's substitute, so write equal negative x over square root 100 minus x squared. Okay, times by the dx dt, which is 4 meters per second. And then the x is 6 meters per second, 6 meters. So we're going to replace both of these by 6. So we get 6, 6. And then we're going to write equal negative 6 over square root 100 minus 6 squared times by 4. Let's use your calculator. I think it will give you an exact value, a fraction. So we go 4 times 6 divided by square root of 100 minus 36. You should get 3. Yep, okay, you get negative 3. The negative indicates to you that it's slipping down, isn't it? Because the quantity y is decreasing. That's why it's negative. So that negative tells you y is decreasing. And since y is decreasing, therefore, it's slipping down, isn't it? The ladder is slipping down. So it makes consistent sense with the question, slipping down. So therefore, you can say slipping down at 3 meters per second. So and sometimes it sounds a bit counterintuitive that this thing's moving at 4 meters per second, but this thing's moving a bit slower, isn't it? At 3 meters per second. So even though they're like sort of connected, it's falling a bit slower than you are falling away. Anyway, that's a question. Okay, good. Let's move on. Okay, so we see different examples of where rate of change are being applied, but they all involve the same thing. The only difference is the formula. So the hard part is get the formula. So we looked at a case where it involves a cone, now it involves a triangle, and then we're going to do a case where it involves 3 variables. Okay, so we're going to skip the next one. The next one is exactly the same. Example 6 is same as example 5. So you could try that a bit later by yourself. Okay, and then we can try example 7. This is a bit different as well. Okay, let's see how that works. This one's actually a little bit harder, even though the wording is very short. But anyway, let's see. Volume of sphere increasing at this rate. So write dV dt is 25 cubic millimeters per second. We've already spoke for almost half an hour. Okay, good. Okay, and then find the increase in surface area, ds dt, when the radius is 150 millimeters. Okay, now this is a question where it involves 3 pronumals. How do I do with 3 pronumals? Do I have to change the formula? Would I have to? So we have to do, okay. So because of this, we need to find the RDT. So even though the question doesn't ask you, let's find the RDT, right? So we have to find, even though we don't have to find, we have to find the RDT in order to find the SDT. So what we do is, since we know the volume, what we're going to do is to first write the dV dt in terms of dV dt. Now, normally you can write ds here, right? That's no problem. But the question is how to find volume in terms of surface area. That's hard, isn't it? We can only find volume in terms of radius. I mean, you could, but it's just too difficult. So that's why we can't do ds straight away. We have to go through the third variable. Okay? It's like in real life that sometimes you have to go through the middle person before you can finish the transaction. The same thing. All right, so we're going to do the RDT. So So we're going to find v in terms of r. So we're going to write v, which is 4 pi r cubed over 3. Okay? All right. So what you do is, then we can find dv over dr, which is 4 pi r squared. I skipped the working out. And then we're going to find the r dt. So we know what dv dt is, which is 25. So we'll go 25 here equals to dv dr 4 pi r squared times dr dt. Now they give you the radius. Radius is 150. Okay, let's substitute 150 in. So r is 150. So we go, so let's make the r dt the subject. The r dt is 25 over 4 pi r squared. Replace that by 150, so we get 25 over 4 pi 150 squared. Okay, so what do we do next? We have to simplify. We have to leave your answer in terms of pi. We want to be exact form, otherwise that will change our answers. So we're going to type in as a fraction 25 over 4 times 150 squared. That thing, okay? 1 over 3,600. 3,600 pi, in terms of pi, okay? Otherwise you get decimal. Okay, in terms of pi, so we've got the r dt. So we're going to highlight that because we will be using this. So I'm going to use a highlighter because this is important. Okay, so highlighter, highlight this bit, which we'll use later on. dv over dt, no, that's the dr over dt. Okay, so we're going to highlight this. Okay, which we'll use later on. Okay, after we do this, we're going to find surface area. So let's find surface area. So ds dt in terms of radius is equal to ds dt, and then put the r there, dr dr. Okay, now we can find ds dt because I know what dr dt is, isn't it? That's the crucial bit. And then the next bit is what's s in terms of r. So you do some working on the side. S, surface area of the sphere is 4 pi r squared. Okay? And then we're going to find ds over dr, which is equal to 8 pi r. That. So we're going to substitute. So we're going to write 8 pi r multiplied by the stuff we just found, which is here. 1 over 3,600 pi. Okay? And the radius is still the same, 150. 150. And then you will see the pi get cancelled, so no problem. Okay, the pi will get cancelled, but don't worry, we'll just do it on a calculator. So you do 8 times 150 divided by 3600. 1/3. Exactly 1/3 units is millimeter square because it's a surface area square per second. Finish. So you can do it with 3 variable as well. In fact, you can do it with 4 variable if you want to. But but you see the ideas. Okay. All right, good. After this, we're going to do one more question. That the next one is a little bit hard. We'll do one more, then we'll finish. Okay. Just one more question. So we'll do the next one, which is over here. Last question. Okay, example 8. Okay, example 8 is a little bit harder. Let's see what that means. Okay, let's read it carefully. A radar tracking station is located at ground level, vertically below the path of an approaching aircraft flying at 900 kilometers per hour at a height of 10,000 meters. Find the rate of degrees per second. The radar beam must be turning at the instant when the aircraft is horizontal distance 3 kilometers from the station. Okay. So what we do is let S represents the tracking station. That's S. And X be the horizontal displacement of the aircraft. So that's X. Okay, so let me see. Oh, we could see just this is also X, which is the same thing. Okay, so we're going to find now. We know what the x dt is. the x dt. Now, because the aircraft is approaching, x is decreasing, isn't it? Because the aircraft is approaching s, x is decreasing, you expect to go, so the x dt must be negative 900 kilometers per hour. So this is 10,000 meters. So let's convert that to kilometers, which is 10 kilometers. Okay, that's 10 kilometers. So you have to make sure everything the same unit. And they want to be per second, but we'll worry about that later. What else are there? Okay, so we have to find the xt. The x dt is given. We have to find at what rate does angle change? The theta dt question mark. Okay, so the question is how to find x in terms of theta, or theta in terms of x. So we have to look at the geometry of the shape, in which case a triangle. So in this case, we have to use trigonometry. So what equation can we write? Let's write an equation. Looks like we can use tan over x equal to tan theta. Opposite over adjacent equal to tan theta. So now we've got an equation that connects x with theta. Okay. All right. So maybe what we could do, let's make x the subject. So write tan equal to x tan theta. So x equal to 10 over tan theta. Yeah, like that. Let's write it like 10 tan theta to power negative 1, because we're going to differentiate in a minute. So therefore, we can write down the related rate. Yep. Continue. All right. So we're going to find, so d theta dt is equal to d theta times d theta times dt, and then put the x here, dx, dx. We know what dx dt is. Good. We have to find d theta dx. So to find d theta dx, you find dx d theta first, and just reciprocal. Okay. So you have to differentiate this. So if you differentiate this, you will get, yeah, you can do it like this, which is negative 10 tan theta to power of negative 2 times tan theta, derivative of tan is sec squared theta. Right, you can do this and then just reciprocal. So that's what you could do. That's one way of doing that. But let's do it in a different way. Method 1, which I will leave you to explore. Let's do method 2. Instead, we can make theta the subject. So maybe we can start from this equation, make theta the subject, which is theta equal to tan inverse of 10 over x. We know how to differentiate inverse function, isn't it? We just learned that in the last topic, and find the theta dx straight away. Let's do that. That will be more useful because I know what x is. X is 3 kilometers from the station. Okay, so find the theta dx, and using inverse tan, so it will be 1 over 1 plus 10 over x squared times by the derivative of tan over x, which is equal to, write that in index form, which is negative 10 x to the power negative 2, like this. So there will be some algebra involved. But you don't have to really simplify everything, because you can just write that as negative 10 over x squared over 1 plus 100 over x squared. And all you have to do, because x is 3 kilometers, isn't it? When it is 3 kilometers from the station. So therefore x is 3. So when x is 3, you can work out. So you can just press the button on a calculator. You don't have to worry about simplifying in a very easy form. Just do it on a calculator, see what we get. So we're going to type fraction and just copy what it looks like, and then put negative 10 over 3 squared, which is 9, over 1 plus another fraction, 100 over 9, equal. Your calculator just give you an answer, which is good, negative 10 over 109, like this. So we got the theta dx straight away. And we found the theta dx. Another approach is the differentiate trick, which can be a bit tricky, but you could explore that yourself. Okay, let's substitute that. Negative 10 over 109 times by dx dt, which is negative 900, and then we'll just do it. So times by negative 900, you get this, 900 over 109, which is positive. Actually, 9,000 over 109. Okay, that will be in radian per hour. Okay, radian per hour. Because every time you involve calculus, the angle is always in radians. Okay, and it's positive because it's turning, isn't it? As you can see, it's turning that way, it's positive. So as the aircraft approaches, the angle increases, isn't it? It turns to the left. But the question asks you to find degree per second. So what you need to do is, let's turn that to degree per second. But before we do that, let's turn it to per second first. So to turn it into per second, you have to divide by 3,600 seconds in 1 hour. So divide that by 3600. 5 over 218. Again, still in radian. How do you convert radian to degree? Times by 180 over pi. Let's do that. 180 over pi. 1.31. Yes, I got it right. 1.31. Approximately 1.31 degrees per second. Yes, so we solved the problem. Okay, so we solved. Okay, now you may be curious, what happens if I proceed with method 1? Let's go through this briefly. Okay, so if you do that, you would have ended up getting negative 10 tan squared theta sec squared theta, isn't it? That's the theta, the dx d theta. So what you need to do is to look at the triangle. Triangle is 3 and 10, that's theta. Using Pythagoras, that will be 9 plus 100, root 109, right? See, that's where the 109 comes from, 109. And then what you do is tan square, that's a sec square. Tan square is opposite over hypotenuse, opposite over adjacent. Sec square is adjacent over hypotenuse reciprocal, which is root 109 over 3 square times by negative 10. Let's see what you get. You will get 100 divided by 9 times by 109 divided by 9 equal times by 10. Hopefully give you a fraction. Oh, very big. I must have done something wrong. Let me see. But hang on, sorry. There's a negative 2. I forgot negative 2. That's a negative 2. So it's actually reciprocal. Let's try that again. So you get 100. It should be 10 times 9 divided by 100 times by 109 divided by 9. That's more like it. 109 over 10. Yep. Negative 109 over 10. So to find the theta dx, which is 10 over 109, as expected, same. So you may like to use inverse tan because it's a bit easier. You don't have to use a triangle. Okay, yep. All right, any questions? So that's all the questions. We spent a lot of time going through all the different types. So you can now start the exercise. The exercise will be from your textbook.